In this video, we'll derive the continuity equation in its differential form. Now, let's start by considering an infinitesimally small control volume with dimensions dx, dy, and dz. That means that if I wanted to take the volume of this small cube, that volume would be dx times dy times dz. Similarly, if I wanted to find the mass of this cube, then my mass should be equal to density times the volume of the cube. Remember, this cube will be infinitesimally small. Okay, we're going to try to picture it as small as we can imagine. We already know that the conservation of mass tells us that the rate of change of mass inside the cube, inside the control volume, is equal to the difference in mass flux entering and leaving the volume. Now, I want you to keep all of these terms in mind because we're going to use them to derive our equation. Let's start with the mass. The mass of the cube is equal to the product of the cube's density times its volume. Expressing the volume in terms of its x, y, and z lengths, the mass should be equal to density times dx times dy times dz, where the density is a function of x, y, z, and time. Of course, we can make assumptions later, such as steady or incompressible flow, in which case the density won't vary, but for now, let's keep the density as a variable. Now, keeping all of this in mind, the mass flux entering the control volume m dot in the x direction should be expressed as m dot in the x direction equals the density term. In this case, let's say that the density enters at a point x equals x, so the density at x times the rate of change in the x component with respect to time, also at position x, times dy dz. Now, this may be a little bit confusing because it's an equation that we haven't seen before, but compare this to the actual expression for mass. We know that mass equals density times dx dy dz, and we know that mass flux is an amount of mass being transferred with respect to time. In this case, all of our numerator terms correspond to the mass of the cube, and the denominator corresponds to a change in time. Because we are moving, there is a flux in the x direction. Anything that's coming into the cube should be taken at position x equals x. Furthermore, we can express the rate of change of x with respect to t as simply my x component of the velocity. Therefore, the mass flux will look as density at x, u at x, times dy times dz. Similarly, we can find the mass flux leaving the control volume in the x direction as mass flux out in the x direction equals the density. Now, because we are taking the mass flux entering the control volume entering at a point x, the mass flux leaving the control volume should leave through a phase that is located at x plus dx. In other words, the mass flux leaving the control volume is equal to the density at x plus dx times the rate of change of x with respect to time at x plus dx times dy dz. Let's look at this equation closely. Notice that dy times dc simply corresponds to the area of the control surface. And also notice that my point x plus dx simply refers to a starting point x plus the displacement in the x direction, which we already called dx. Let's rewrite this expression so it looks similar to the one above. We have the density at x plus dx multiplied by the x component of the velocity at x plus dx multiplied by the area of the control surface, which is dy and dz. We can apply this in the y direction and in the z direction similarly, and we can insert these back into our conservation of mass equation. So I'm going to try to write them down. In the y direction, we should have density at y times the y component of velocity at y times the area of the control surface, which in this case should be equal to dx dz. For the mass flux leaving, we should have density at y plus dy times y component of the velocity at y plus dy times the area of the control surface, which is dx times dz. We can do the same for the z direction. So, expressing my mass flux entering and leaving my control surface in terms of its x, y, and z components will allow us to insert all these terms into my mass flux entering minus my mass flux leaving. So let's do that. We know that the mass flux entering the control volume should be equal to the x component of the mass flux entering, the y component of the mass flux entering, and the z component of the mass flux entering, where the x component can be found here, the y component is written here, and the z component is written here. To this, we will subtract the x component of the mass flux leaving the control volume, the y component of the mass flux leaving the control volume, and the z component of the mass flux leaving the control volume. And following the conservation of mass, this should be equal to the rate of change of mass in my system. Now, we're going to insert all of these answers into this equation, which means that this is going to take a while and the equation may look a little bit long. But it is worth it because in the end we will try to simplify this equation as much as possible into one that we can actually apply to solve engineering problems. So let's go ahead and do that. I'm going to try to keep my x terms in red, my y terms in blue, and my z terms in green, just so that you don't get lost. There we go. So we've taken a generally simple equation, conservation of mass, and we've expanded it into this monstrosity. However, we are going to find ways to simplify this monstrosity into another simple equation. But for now, let's turn our attention to the change in mass. We know that the change in mass dm with respect to time can be expressed as the change in the product of density times the volume with respect to time. Now, our volume doesn't really change with respect to time because our control volume is fixed. And when we find the change in density with respect to time, we already mentioned that density was a function of space and time. So we can't really take an ordinary derivative or a total derivative. We instead take a partial derivative. So we take out the volume because it is a constant, and we end up with the partial derivative of density with respect to time multiplied by the volume that we took out of the equation. Okay? Now, this will allow us to insert this term into our continuity equation. Looking at what we have in the equation so far, you'll notice that we have a couple of common variables across all the terms. These common variables are the lengths of the sides of our control volume, dx, dy, and dz. So let's try to write down this equation, and let's divide everything by dx, dy, dz. So what do we have? Dividing both sides by dx, dy, and dz will cancel out the volume term on the right side of the equation. It will also cancel out the area of the control surface on the left term of the left side of the equation, but we will be left over with one length scale of the control volume. In this case, dx and dz are cancelled out, but we are left with dy. In this case, dx and dy are cancelled out, so we are left with dz, and so on and so forth. Now we can further rearrange this equation. Let's try to keep all of the terms that have dx in the denominator together, all the terms that have dy in the denominator together, and all of the terms that have dz in the denominator together. So I'm going to start by combining my terms that have dx in the denominator. Those are Now I can combine all of my terms that have dy in the denominator. And similarly, I can combine all the terms that have dz in the denominator. Now the sum of these three new terms should be equal to the partial derivative of the density of the fluid element, in this case the control volume, with respect to time. Now, hopefully this equation will look somewhat familiar to you. From calculus, we know that the derivative of a function u with respect to x can be found by limiting du over dx as given that our fluid element has an infinitesimally small volume, so it has infinitesimally small dimensions, then we can apply this definition of a derivative into our terms in the continuity equation. In this case, we will have that the derivative of my function u, which would be my pressure times my velocity component for a fluid particle with respect to the x direction. Now notice a couple of things. In our definition for a derivative, the one that we learned from calculus, our derivative is found by taking the value of the function at a second point and subtracting that from the value of a function at a first point. We have the opposite here, which means that our derivative in the continuity equation will have a negative sign because it is the same as applying a negative sign to our definition. That being said, let's apply this rule from calculus into our continuity equation terms. We will get that the x terms in our continuity equation should be equal to the derivative of pressure times u with respect to x, density times u with respect to x. However, keep in mind that density and velocity don't just vary with respect to one variable, they vary with respect to space and time, which means that the derivative that results from this term should be a partial derivative, not a total derivative. In other words, we will get partial derivative of density times the x component of velocity with respect to x. Since we are applying a negative sign in order to end up with our initial term, we need to apply a negative sign to our derivative. When it comes to our y term, we will have the partial derivative of density times the y component of the velocity with respect to y. And when it comes to the z term, we will have the partial derivative of density times the z component of the velocity with respect to z. Applying this into the continuity equation, we have that these three terms should be equal to the rate of change of density with respect to time. keeping in mind that the rate of change of density with respect to time will be a partial derivative. We can further rearrange this equation to look as follows. And now our continuity equation is starting to take some form in the differential form. Notice that we have a partial with respect to x plus a partial with respect to y plus a partial with respect to z applied to the x, y, and z components of the velocity vector respectively. Now we've seen this before. The application of a partial of an x component with respect to x plus a partial of a y component with respect to y plus a partial of a z component with respect to z is also known as the divergence. In this case, these three terms represent the divergence of the density times the velocity vector. So we can express our continuity equation as partial density with respect to time plus del dot density times velocity vector equals 0. And this is our continuity equation in its differential form. Notice that it actually looks very different from the equation that we derived from an integral point of view. However, both equations that we've derived actually say the same thing. A different notation for the continuity equation will be to take density, and the variable by which we are deriving it can be expressed as a subscript. We can also express the divergence as just div of my vector field equals 0. So this is an alternative way of expressing the continuity equation. You may see either one of these or both in different textbooks. So that's it. That's a derivation of the continuity equation in its differential form.